everyone, my name is Amanda Rösler, and today I'm going to talk about how we implemented a save system for an open-ended gardening and exploration game in Unity. I'll start with a quick introduction. I'm a game programmer from Sweden, and I've worked in the game industry since 2011. I'm currently the lead programmer on a VR game called Garden of the Sea. I work at a small indie studio in Stockholm called Neat Corporation. We currently have 11 employees, and the studio is focused on making VR games only. We released our first game, Budget Cuts, a few years ago. It's a stealth action game where you need to sneak around and throw knives at robots. This became pretty popular, so we made a sequel that was released last year. But simultaneously, we've also been working on a completely different game, Garden of the Sea. I'll show a short trailer so that you can get a feeling for the game. Like I said before, Garden of the Sea is made in Unity, and it's currently out in early access on Steam. There are many different things you can do in the game, but I would say that the core loop of the game is about gardening, exploration, and crafting. You start out on an island with just a tent and a few tools, and you need to explore the area to learn how to grow plants and vegetables, craft useful items, and upgrade your tent to a house, among other things. You can also build a boat that can be used to travel to other islands, where you can gather different types of resources. So what are some of the challenges when developing a game like this? It's a large world with different areas that need to stream in and out. There are lots of dynamic objects, there are lots of different types of objects, and players can create and destroy objects at will, for example through crafting, planting seeds, and composting. So the question is then, how do you save the game state when you have such a dynamic world? When we implemented the first version of the save system, we didn't have a lot of time to do it since we had a deadline that we needed to meet. So we decided to just take the save system from Budget Cuts and integrate that into our project. In hindsight, that might not have been the best idea. The way that system worked was that whenever an object was spawned or removed during gameplay, that object would be marked as added or deleted in the save file. Then when you loaded a save, it will load in the scene as usual and then remove those game objects that were marked for deletion. And then it will also spawn in the objects that needed to be added. We had a lot of issues with this system, and I'll go into more detail about that later. But to summarize, we realized that this approach wasn't really suitable for a game where you constantly create and destroy objects. Budget Cuts is, after all, a very different game. It's much more linear, so it also has different requirements when it comes to saving and loading. So we decided to implement a completely new save system with the goal of making it more flexible and easier to use. And as I was doing this, the task grew to become more than just a save system, because it was such an integral part of the code that it influenced a bunch of other systems. So I also ended up making a spawn manager, a system for initializing components, and a system for streaming in new areas. Let's go into detail about some of the things we did. At first, we had just one big scene that contained everything in the game. We decided to split that up into multiple scenes that could be loaded additively. First, we put each of the islands into a separate scene. And then we split those up into two additional parts. One static scene and one dynamic scene. As you can probably imagine, the static scene contains all the static meshes, but also some other things like quest logic, spawn points for creatures, some characters, and other things that should always be present in the area. The dynamic scenes contain objects that you can move and interact with, like plants, crafted items, and other resources. In other words, everything that can potentially be destroyed by the player. There are two main reasons for why we wanted to do it this way. First, we didn't want to keep track of all the items that had been removed from the game. Instead, we decided to just save a list of all the objects that were still alive, so that when we loaded a save file, we could just spawn those objects directly without needing to load the dynamic scene at all. The second reason was that when a player travels to a different island, we wanted to be able to load in the static scene first, so that the silhouette of the island would become visible. And then we could load in all the small dynamic objects as the player got closer. But in order to implement this idea, we needed to figure something out. How could we serialize a reference to a prefab in the save file? One option would be to save the path to the prefab and then load it using resources.load. But that wouldn't work if someone renamed the prefab or moved it to a different folder. So that seemed like a bad idea. It would be convenient if we could use the unique ID that each asset has in the asset database, because that doesn't change if we move the file around. But of course, that's not an option because you can't use the asset database to load it during runtime. We did some research and we figured out that this might be a good use case for the addressable assets system. In case you don't know what that is, I'll explain it quickly. The addressable asset system, or addressables as it's sometimes called, is a package provided by Unity. And the purpose of it is to provide an easy way to load assets asynchronously. Each asset is identified by a globally unique ID and an address. This address can be changed at any time by the user, but the ID, on the other hand, is persistent and doesn't change. And by the way, this is the same ID as the one in the asset database. You can choose to load an asset either by address or by ID. But we wanted to use the ID since that's guaranteed to not change. And to do that, you need something called an asset reference. This is an object that can be created from the unique ID, or by directly assigning an asset to it in the inspector. Let's continue with the rest of the save system. This is an example of what a prefab might look like in our game. The object has a component called SaveObject, which in turn has references to 3 other components: grabbable, stashable, and paintable. Those 3 components all inherit from a base class called SaveAble, which means that they want to save some data in the save file. This is what the beginning of the SaveObject component looks like. As you can see, it has something called a save ID. This is a custom class that contains a unique ID that will be used to identify this instance in the save file. It also has an asset reference, like we just talked about. This is a reference to the prefab that this save object is part of. And then there is the array containing the savable components that belong to the save object. That array is automatically populated and saved when you edit the prefab, so that we don't have to call getComponent to find them during runtime. This is how the save file is structured. It has one list that contains the save IDs, asset references, and transforms for all the dynamic objects. There is a separate list for the static objects, and they only need the save IDs and the transforms since they won't be spawned in, and they're always part of the scene. And then there's another list with all the data for the savable components, coupled with the relevant save ID so that it can be applied to the correct object. All of this is saved as JSON, by the way. Then we also have some additional binary data that's needed to keep track of where the player has dug and watered the soil on the ground. I want to go into a bit more detail about the savable component. Like I said before, all scripts that need to save some data inherit from savable. It has an abstract method called createState that the child classes need to implement. CreateState should return an instance of a class called SaveObject, or a class that inherits from it. The savable state should only contain the data that needs to be saved, no logic. This data will be converted to JSON when we save. Here's an example. We have a watering can in the game, and it needs to save how much water is left in it. So watering can inherits from savable, and it implements createState, which returns a water state. And water state inherits from savable state. So createState will be called when the player saves the game. Additionally, it will also be called the first time this object is loaded to set up some default values for it. This is what the water state class looks like. All it has is a float that represents the amount of water and a constructor. In the save file, it will look something like this. It has the save ID, so that we know which object it belongs to. It has the savable component type, so that we know which component to apply it to. And it has the water state itself. This is part of what the base class SaveAble looks like. It has a method called initState that takes a savable state. When this object is created for the first time, we pass in null to initState, which will cause it to call createState, where the object can set up the default values. If we're instead loading a save file, we pass in the savable state from the save data. Each class that inherits from savable should also implement a method called Initialize. This is called after initState is called, which means that the object can read the savable state here and then do some logic based on that. Just to make it clear, this is what happens when you start the game or load an area for the first time. So first we load the static scenes, then we load the dynamic scenes, then we call initState on all the savables, and we pass in null so that it in turn will call createState. Then we call Initialize on all the savables. This is what happens if you load a save file. First we read the save file data from disk, then we load the static scenes as usual. Then we spawn in all the dynamic objects that were in that area. Then we take the savable states from the save data and pass that to initState on all the savables. And finally, we call Initialize on all the savables. Let me explain our reasoning behind this. When Initialize is called, it's guaranteed that the object has been assigned its initial data, whether that's the default data or data from a save file. In the old save system, we used to have some logic that happened in awake or on start, and then some other logic that happened when you loaded a save. And that sometimes made the code a bit confusing and buggy. So we wanted to have all the initialization logic in one place, and not be dependent on whether you're loading a save file or starting a new game. It's also guaranteed that by the time Initialize is called, all the other objects in the same area have also been spawned. So that makes it easier to handle dependencies between objects. It's also possible to specify the order in which the different types of savable components are initialized, in case you have dependencies between the different components. I also want to talk a little bit about why we chose to use JSON as the format to save the data in. In the old save system, the code for saving and loading might look like something like this. You need to carefully serialize and deserialize the data in the correct order, which meant that if you refactored your code, it would probably break your previous save files. When using JSON, on the other hand, you can take a serializable class and convert it directly to JSON and back again, like this. This even works if you add, remove, or reorder the variables in your serializable class, which can make it easier to maintain compatibility with save files from older versions of the game. JSON is also nice because it's human readable, so you can easily open up a save file and look at the values directly. The main drawback of JSON is that it is kind of slow, since it converts everything to strings. It might also result in larger save files, depending on what you compare it to. I measured that it takes around 40 milliseconds to convert the save data to JSON when I had 700 objects in the game. And that's not too bad if it happens during a loading screen, but we want to avoid loading screens during gameplay. And the size of the save file is roughly 2 megabytes of JSON data, plus an additional 3 megabytes of binary data for the soil state, like I mentioned before. Let's move on to streaming. There are a few things that we need to take into consideration for the save system when we stream in new areas. First of all, when the player takes the boat and goes to a different island, the previous island will be unloaded from the game. And that means that we have to save the state of the previous island before that happens, obviously. To make this easier to handle, we store the save data for each area separately. We also save which areas are currently loaded, so that we know which areas to load the next time the player starts the game. But what if the player brings an item with them on their boat and goes to a different island? Then we have to move that game object from its original scene to the new scene. Otherwise it will get unloaded when the player gets too far away from the island and the scene gets unloaded. And we also have to make sure that we associate the item's save data with the new area. Otherwise it won't get spawned in the correct area. So we have some ideas for how to further improve these systems. The main thing that we want to do is reduce the time it takes to save the game, so that we can avoid frame drops. And one idea is to make it possible to save incrementally over several frames, either by time boxing the save operation or by moving the JSON conversion to a background thread. We also want to look into BSON and other binary formats, at least for when we go out of early access. BSON is a binary version of JSON that's supposedly faster, so that might be a good fit for us. We might also consider compressing the save file, especially when we add even more objects to the game. And that's all I have time for today. Thank you everyone for listening. And now it's time for questions.
Thank you for your talk, Amanda. So questions. So as understood, that system works in such a way that you save progress for each island separately, right?
Yeah, that's correct.
So so it must work better in terms of optimization, because when you enter new island, you need to get progress only for it.
Yeah, exactly. Yeah, that's one of the reasons why I did it this way.
Okay, and how much time does it usually take to get progress for one island?
I don't have the measurements right
Like
now.
roughly.
I mean, it takes. I mean, like I said in the slides, it's like it's several frames. That's for sure. It could be optimized, and you know, in VR, we have to run at 90 frames per second, so it's even more difficult to get it to run smoothly. But I'm still working on improving it.
But I mean, you don't show any kind of like progress bar of loading new island.
No.
So it's just happening on time. But that's anyway good if it like if it works good enough to be released in such a way. That's I think it's quite good result of what you do. Okay, and but that's only, as I understood, that's only about saves. What about resources themselves? I mean, when you enter a new island, you need not only, as I understand it, you need not only to load your progress, but also to load necessary resources for that island, or not?
Yeah, exactly. You need to spawn in all the objects on the island. So, I mean, that also takes some time.
Uh-huh. Okay, I got it. Tell us about your plan for this project. When do you think it will be released?
Oh, I don't think we have like an official date. I mean, it's out in early access now, and we're releasing updates like every few months. But I would estimate that it will be like it will go out of early access in a year, maybe.
Mm-hmm. Okay. Sounds great. Good luck with it.
Thanks.
We have a question from audience. How much time did it take for you to implement that system?
Oh, I think it took a few months, like 2-3 months. And like the main reason why it took so long is because we had to like redo all the saving and loading mechanic for all the like the different types of game objects that we already had. So that was quite a lot of work. And
so you needed to support that architecture for all the stuff, right?
Yeah.
Okay, that makes sense. Okay, so you don't have any more questions, neither from me nor from audience. Thank you very much for your talk.